Chapter 9, Describing Performance with Numbers. In this chapter, recognizing different types of data, understanding the basics of statistics, and seeing the difference between short-term and long-term variation. Although the idea of data, numbers, and measurements may not be exciting to some, it should be very exciting to you, as a Six Sigma practitioner who is tasked with improving a process, an operational unit, or an entire organization. In this chapter, you find out about different types of data and understand how to characterize data in a critical, scientific way. The nitty-gritty information in the following sections can help you use tried and true statistical tools to explain how your processes are performing. Recognizing different types of data. All data aren't created equal. All data isn't created equal. As you begin your quest to organize your data, you first need to know what type of performance data you have. Just as knowing what the fish are biting tells you which lure to use, knowing what kind of data you're dealing with tells you which tools to use. This section defines two important data categories: attribute, also known as category, and continuous, also called variable. Take a look at them in Table 9-1 and the following sections. Okay, so this here is Table 9-1. Identifying attribute or category data. Some data consists of measurements that describe an attribute of the characteristic or process. This data is called attribute or category data. If you're watching this, the book uses the plural of data in like bizarre ways that I'm not used to. It says these data are called attribute or category data, which is insane to me. It should say this data is called attribute or category data. Like, it makes me want to vomit every time I see it. So that's what you're seeing. I digress. Attribute data are all around you. Telephone area codes, small, medium, large, extra large, XXL clothing sizes. Pass or fail judgments pronounced on just assembled products. Good or bad assessments of the output from a process. How do you know whether you're working with attribute data? The telltale test is to ask yourself, can I meaningfully add or subtract values of this data? If the answer is no, what you have is attribute data. For example, what do you get when you add an S-sized shirt to an M-sized shirt? Nothing meaningful. Or if you subtract telephone area code 213 from area code 415, does the resulting area code of 202 mean something? Of course not. And so you know that you're dealing with attribute data. What you can do with attribute data is count how many times each category or attribute appears. For example, you may find that a process produces 152 good items and 28 bad items over a given period of time. You use the results of these types of category counting studies as the starting point for many Six Sigma analyses. A subset category of attribute data that provides a little more horsepower is called ordinal data, also known as rank order data. Ordinal data is attribute data that can be logically placed in an order from smallest to greatest or in an order of time, such as the months of the year, January, February, March, and so on. If you have month data on a set of last year's invoices, you can sort them into buckets of occurrence starting with January and then move on through the year. Or you may not have actual completion times, but you may have data about which employees finished the task first, second, third, and so on. In this case, you have a powerful set of ordinal data that you can use to begin analysis and improvement. Classifying continuous or variable data. If you find that you can meaningfully add or subtract any two values of your data, you're working with continuous or variable data rather than attribute data. See the preceding section for more on attribute data. When testing whether data is attribute or continuous, be sure to apply the meaningfully add or subtract the values question to the raw data and not to any summarized counts of the data. For example, the fact that you can subtract 5 medium-sized shirts from 7 large-sized shirts to get a 2-shirt difference doesn't indicate that you have continuous data. You have to apply the question to the raw data. An L-size shirt minus an M-size shirt has no meaningful answer. Technical stuff. Both continuous and variable are poor names for this type of data. But for whatever reason, these are the names that have stuck. The name continuous is meant to convey the idea that this data type can have any value from a continuous scale, like the reading on a mercury thermometer. Variable is an attempt to say the same thing, that the measured values can vary anywhere along a given scale. You can get a 98.23 degrees Fahrenheit, or 98.25 degrees Fahrenheit, or a 98.37 degrees Fahrenheit. The problem is that no matter how continuous or variable you think the measurement scale is, as soon as you record a measurement, you always truncate its reading to some fixed length, making it no longer continuous. But the powers that be want you to use the names continuous and variable, so go ahead and use them anyway. A few more examples of continuous data include a numbered GPA scale representing letter grades at school, the temperature in your own room, in your oven, the amount of money you spend on groceries, the time it takes to complete a processed task, the gas mileage of your car. Any two values of continuous or variable data can always be meaningfully added or subtracted. For example, a count on the number of children in each household can only occur in integer values. You can't physically have 2.3 children. So the scale of measure of children in a household isn't continuous at all. But you can take the integer measurement from each household and perform mathematical operations to calculate a meaningful average or standard deviation. Being able to mathematically operate on any two values of continuous data is what sets it apart from attribute data. Using statistics to make sense of data. In 1891, the famous scientist Lord Kelvin provided valuable insight for future Six Sigma practitioners. When you can measure what you are speaking about and express it in numbers, you know something about it. But when you cannot express it in numbers, your knowledge is of a meager and unsatisfactory kind. It may be the beginning of knowledge, but you have scarcely in your thoughts advanced to the state of science. In other words, if you want to make big performance gains, you need to harness the power of statistics and data analysis to take you out of the realm of intuition and estimation and into the realm of objective truth. Statistics and its embodiment in Six Sigma is like vegetables. It's not always what you want to have, but you know it's good for you. Statistics is the branch of mathematics that distills raw numbers, data, and measurements into knowledge and insight. If you understand a little bit about statistics, you can create a data leveraging environment that you can use to understand or improve something. You don't have to have a PhD in statistics to be a Six Sigma practitioner, but you should have a grasp of the statistical concepts that we cover in this section. Armed with two quantities, a measure of location and a measure of spread, you can describe any type of distribution in scientific terms. Lord Kelvin would be proud. Beginning with measurement 101, distribution. Suppose you need to find out how long filling out a certain purchase order form takes. Each time you fill out the form, you record the elapsed time to the nearest second and plot the result as a dot along a horizontal timescale. Figure 9-1 shows the first 3 times you fill out the form with times of 41, 50, and 47 seconds. See how your data reveals that variation is inherent in the process? Continuing the study, you take a total of 100 purchase order time measurements. Whenever you encounter a measurement that already has a recording, such as 47 seconds, you simply stack another dot on top of the previous dot. Figure 9-2 has the completed chart with all 100 measurements. Okay, so here's figure 9-1. Figure 9-2. Notice in figure 9-2 that the output values that occur often pile up with multiple dots. For example, 50 seconds is the purchase order completion time that occurs more frequently than any other. Consequently, it has the highest peak in the chart, 15 occurrences. Output values that happen less frequently have lower heights, and output values that were never observed have no dots at all. Figure 9-2 graphically describes how the measured output is distributed along its scale of measure, time. Looking at the chart, you can predict that if you were to measure another cycle of the purchase order process, the elapsed time would most likely be around 50 seconds. A completion time of 30 seconds or 80 seconds, for example, is just not likely to happen. Distribution is the statistical term that describes the relative likelihood of observing values for a variable factor. You may also see it referred to as probability distribution or probability density function. When you think of the critical performance characteristics of a product or service, either output Y's or input X's, you should begin thinking of them as distributions. Variation is inherent in all X's and Y's, so you will see distributions in your measurement. Measuring distribution location. When you have a distribution for some data you're working with, check out the preceding section for an example. You can then ask yourself, how can I describe this distribution with numbers? Or, where is the distribution center located along the scale of measure? A distribution can have infinitely many points, and fixing a location for the distribution is important so that you can then understand the variation around the location. To determine this section, statisticians have developed 3 different measures of central tendency to describe a distribution's location: the mode, the mean, and the median. Table 9-2 gives you an overview of these measures, and we discuss them more fully in the following sections. Table 9-2, okay. Evaluating peaks a la mode. The mode is the value observed most frequently in a distribution and is associated with the distribution's highest peak. If 10 students take an exam and 3 score 60, 3 score 90, 4 score 80, you peg 80 as the mode because it occurs more frequently than any other value. Although using the mode as the measure of variation location is simple and intuitive, doing so has a drawback. Many distributions don't have a single clear peak, and some have more than one peak or roughly the same height. In these cases, presenting a single mode metric by itself does little to deepen your knowledge of the location of the variation. Making nice with the mean. The most common measure of central tendency is the mean, widely called the average. Examples of averages are everywhere. The Dow Jones Industrial Average, grade point average, the average temperature in your hometown, and the list goes on. Understand that the mean is theoretical rather than real. Although the mean may not have actually occurred within your measurements, it's the value most likely to occur next in a sequence or population of data. The mean, therefore, is a mental model by which the Six Sigma practitioner, that's you, can make comparisons, forecasts, predictions, interpret data, and anchor much of the analytical work that is done in order to save money in operations, make customers more satisfied, and improve products and services. Calculating the mean is simple. Imagine having 10 paper cups, each holding a different amount of water. What is the average amount of water in the cups? Consider combining the contents of each of the 10 cups into a large bowl. You'd simply measure the collected amount and divide it by the number of paper cups. This tells you how much water would be in each paper cup if the amounts were forced to be equal, or average. Mathematically, the process for calculating the mean is written as summation of average equals summation of x sub I over n. Forget these words. Forget what they mean. Where X pronounced X bar is the symbol representing the calculated mean. E is the Greek capital letter sigma. In the shorthand of math, it tells you to sum up or add all the individual measurements. X sub I represents each of the individual measurements, and N is the number of individual measurements in your data set. So for the purchase order form example in figure 9-2, you find the mean, or X bar, by adding up each of the N equals 100 time measurements and dividing the result by N equals 100. The result is an X bar of 49.9 seconds, or an average of 49.9 seconds. Computing the math for any distribution is never any harder than that. Finding the median. The median is the point along the scale of measure where half the collected data is below and half is above. The median is the preferred measure of variation location when your collected data contains outliers, recorded observations that are well outside the range of variation of the rest of the data. For example, the median is often used when communicating home prices because it's usually more reflective of the central tendency of the distribution of all prices. Suppose you have a set of homes with prices of $158,000, $200,000, $178,000, $125,000, and $535,000. The average price is $239,200. The median, however, is $178,000. Figure 9-3 shows the raw data of home prices with the mean and median specified. Note that the median represents the central location of the distributed home prices better than the mean does. That's because the calculated value of the mean is pulled up away from the more accurate location value by the presence of the outlier, the $535,000 home. Beware when someone communicates only the average of a measured characteristic to you when describing its performance. Without your knowledge, he or she may have included an outlier, accidentally or on purpose, that has biased the calculated mean value. Here's a little graph to show you. Calculating the width of variation. Measures of mean, median, and mode don't tell the whole story. They fail to communicate exactly how spread out or widely dispersed the variation really is around its central location point. For example, two sets of measurements with identical means may contain raw data values that are distributed very differently. You need a second measure to quantify how widely or narrowly dispersed the data are around their central location. In this section, you find out how to do that with the range and standard deviation. Check out table 9-3 to get an idea of these measurements. Here's table 9-3, which is some random equations. Okay. Working with the range. The simplest measure of the spread of your data is its range. The range of a distribution is defined as the difference between the largest and the smallest observed data values. Mathematically, you write this quantity as R equals x sub max minus x sub min, where R is the calculated range, x sub max is the largest observed measurement, and x sub min is the smallest observed measurement. In the figure 9-2 form example, see the section beginning with measurement 101 distribution for the full example. The range is simply the longest recorded time to fill out the form, 60 seconds, minus the shortest recorded time, 41 seconds, or R equals 19 seconds. Calculating the range works just as well when you only have 2 recorded measurements as it does when you have 1,000. But obviously, outliers directly affect its calculated value. By their very nature, outliers end up being the x sub max or x sub min used to calculate the range. Determining the standard deviation. So, can you quantify a distribution's degree of dispersion in a way that avoids the problem of outliers. Look at any single recorded measurement. How far is it from the central location of the data set? Mathematically, you represent this problem as x sub I minus x bar, where x sub I represents any single recorded measurement from your data set, and x bar is the calculated mean of your collected observations. Xi minus x bar then acts as a numerical score for each data point. Like in golf, the lower the magnitude of the score, the better, the less it varies from the central location. You've probably played around with numbers enough, however, to recognize a problem with this scoring system. When x is less than the mean, the score ends up being less than 0. That won't work as a way to fairly score the distance of each point from the average. Being above or below the central location doesn't matter. It's how far away it is that counts, and negative scores make things too complicated. You need a way to score each data point that looks only at the data point's distance from the central location and disregards the direction of the distance. Luckily, you can get around this problem by using the following formula. X sub I minus x bar squared. The parentheses and the exponent 2 tell you to square the entire quantity. X sub I minus x bar. Multiply x by itself. No matter whether the quantity you're squaring is positive or negative, the resulting answer is always positive. 2 times 2 equals 4, and negative 3 times negative 3 equals 9. Thus, you've taken care of the negative number issue. A side benefit of squaring each individual score is that it penalizes points that are farther away from the central location disproportionately more than those that are closer. Figure 9-4 shows a plot of x sub I minus x bar squared output values versus input values for x sub I minus x bar. Right there. If an individual data point is 1 unit away from the central location on either side, x sub I minus x bar equals 1, and x sub I minus x bar squared equals 1. If a different point is 2 units away, however, x sub I minus x bar squared equals 4, resulting in a score that isn't twice as bad as 4 times as bad. To create an overall combined score for the entire data set, simply add all the individual squared across scores together. To create an overall combined score for the entire data set, simply add all the individual squared scores together. Mathematicians write this operation as sigma x sub I minus x bar squared. Summation x sub I minus x bar squared. It's fine. Statisticians call this result the summed squared error, or SSE for short. In the field of statistics, error doesn't mean something is wrong. The term simply means a calculated deviation from a comparison value. In this case, error is the difference between the mean and the individual observations. To find the average squared score, you divide the summed squared error by the number of independent data points in your collection like this. Equation. Like this equation right here. Where n is the total number of data points you've collected, something squared is the average squared error score, error squared, what statistician called the variance. Right now, one of two things has happened. Either your eyes have glazed over, or you're saying, hold on a minute, why did you divide by 1 less than the number of measurements I collected in n minus 1, rather than by the total I collected n? That doesn't seem right. If you're in the latter camp, you've asked an outstanding question. And if you're in the former camp, don't worry, statistics does that to the best of us. Notice that the equation for the variance includes the mean, x bar. This point is where you lose the independence of one of your collected measurements. It's like having a full 5-gallon bucket and dividing the contents completely into 10 new buckets. Even though the amounts you pour into the first 9 buckets can vary independently from each other, when you get to the 10th bucket, you have no more freedom. What you have is exactly what remains. In the same way, using the mean reduces the number of independent measurements available to compute the variance. Okay. Finding the standard deviation. A final problem lingers with the development of a measure of how widely or narrowly your collected data is distributed. What are the units associated with the computed variance? In the figure 9-2 purchase order example, your measurements have been in seconds. That means the variance comes out as seconds squared. In the real world, no one knows what seconds squared are, and anyone who thinks they do ought to be avoided. The person who originally solved this last issue must have known the answer from the beginning. Notice that the symbol for the variance is error squared, or whatever that symbol is squared. And as you've likely guessed, the solution is simply to reverse the squaring done previously to your measurements. Mathematicians call this reverse squaring operation the square root and give it a special operator symbol, square root. Applying it to the variance introduces the measurement you're after, namely the standard deviation. Oh, it's called standard deviation. That's the symbol that I'm forgetting. Standard deviation equals the summation of x1 sub 1 minus x bar squared over n minus 1 square root of the whole thing. Okay, great. The standard deviation is by far the most commonly used measure of dispersion. It occurs throughout statistics and Six Sigma. That's where this whole quality initiative gets its name. The standard deviation represents the typical average distance from the central location you expect to observe. Its units are exactly the same as your original measurements. So, for the purchase order example, its units are seconds. The long and short of variation. In the earlier section, using statistics to make sense of data, we introduced the various measures of variation. This section continues the topic by peeling back the layers of the onion to reveal another aspect of variation you need to know about, the difference between long and short-term variation. For quick reference, Table 9 presents the formulas for both of these types of variation. The following sections cover deviation in detail. Here's Table 9-4. Sizing up short-term variation. Suppose you monitor a characteristic of a product or process, say the volume of inbound calls per hour at a customer call center, over an extended period. Each hour, you measure and record the number of calls received. To review what you've observed, you graph your collected measurements as a sequence of connected points along an axis representing time, as shown in Figure 9-5. Although the points graphed in Figure 9-5 represent the number of incoming calls per hour, recognize that they can also represent any process characteristic in any type of company. All process characteristics vary from cycle to cycle. The exact length of newly manufactured pencils, the time required to fill out an invoice, the number of calls per hour, and so on. If you zoom in on a narrow portion of the graph, as shown in Figure 9-6, you can see from the scattered points that the output certainly does vary for each measurement cycle. But you can also notice that the variation isn't limited. It lies within upper and lower boundary limits, represented by the dashed horizontal lines. Here's one of them. It's one of them graphs. In fact, for any selected short period of time, the process essentially varies within the same rough limits. Try it for yourself. Pick any short time segment of Figure 9-5 and eyeball the vertical variation limits with your thumb and index finger. Now, keeping the distance between your fingers fixed, move to a different time section of the graph. Do your eyeballed limits capture the output variation for other short-term segments? This natural level of variation is called the short-term variation of a process. Often, it's designated with a simple ST notation. Short-term variation is purely random. Like rolling a pair of dice, you can't predict what the next output value will be. If you could, Las Vegas would be bankrupt in a week. Short-term variation, sometimes called entitlement variation, is what you use to compare the inherent capability of different processes to meet a specified goal. For example, creating a shaped plastic part by using an injection mold machine may have an entitlement variation of plus or minus 0.002 inches. The process of cutting plastic with a milling machine, on the other hand, may have an entitlement variation of plus or minus 0.0005 inches. In this case, the milling machine process has a better level of entitlement. It has less inherent short-term variation. Considering the many causes of short-term variation. Short-term variation is caused by the combined effect of all the little things that are too hard to include in your understanding of the process. Even Einstein would find it too difficult to determine exactly how the microscopic textures of the dice contribute to their spin as they contact the felt surface of the table, or how the drag of the swirling air on the corners of the airborne dice alters their tumble. These factors, and many more, are real and do add up to affect the outcome of the roll. The reality of short-term variation in any and all processes, from rolling dice to preparing a meal, to writing a memo, to launching a rocket, is that the complete chain of causation is unknown and unknowable. Like rolling dice, your ability to understand the full depth of causation for any process is ultimately limited. Because these small forces are present to some degree in all processes, they're referred to as common. Consequently, the short-term variation they cause is sometimes called common cause variation. Calculating short-term variation. After you know what short-term variation is, you need to know how to quantify it. The formula in the earlier section, finding the standard deviation for calculating the standard deviation, doesn't account for any short or long-term effects. It just looks at the overall variation in all the measurements. But never fear. Hardworking statisticians have developed a way to extract the level of the short-term variation out from the overall variation. The quickest way to get to the short-term variation is to analyze the separation or differences between sequential measurements of a critical characteristic. The difference between any two sequential measurements can be thought of as a kind of range. For a sequence of measurements, x, x1, x2, x blah blah blah, where n is the total number of collected data points, you can write the difference or range between the first and second measurement as r equals the summation of x sub 1 minus x sub 2, or no, the absolute value of x sub 1 minus x sub 2. In general, the difference between any two sequential measurements is r sub I equals the absolute value of x sub I minus x sub I plus 1. X sub 1, x sub 2, x sub 3, all the way to x sub n minus 1 to x sub n becomes r sub 1 equals the absolute value of x sub 1 minus x sub 2, and so on, x1. The vertical parentheses like bars in the equation are called an absolute value. They signal you to take the positive magnitude of the calculated difference inside the absolute value symbols, regardless of whether it is a positive or negative value. And the average range or difference between sequential points is r bar equals 1 over n minus 1 times the summation from I equals 1 to n minus 1 of r sub I. I might have to take Calc 1 for fun. The way to calculate the short-term standard deviation from these sequential between-point ranges is to multiply their average by a special correction factor based on the range between two sequential measurements. What was that fucking O called? Standard deviation. Standard deviation. Okay. So the standard deviation sub ST equals R bar over 1.128. Obviously. Never try to calculate a characteristic's short-term standard deviation on anything other than a sequential set of measurements. That is, only perform this calculation on a set of measurements that are in the exact order that the measurements were taken. The calculation of the short-term standard deviation is based on the natural ranges that occur between the characteristics measurements. Altering the order of the measurements in any way directly affects the calculated value of the short-term standard deviation. Shift happens. Looking at long-term variation. Take another look at the extended process behavior graph in figure 9-5 earlier in the chapter. Something besides pure random variation is going on here. Notice that the range of short-term variation doesn't stay locked at a single level. Instead, it shifts and drifts up and down over time. These bumps and currents, called disturbances to the process, are emphasized with overlaid lines in figure 9-7. When these underlying disturbances are added to the natural short-term variation, the overall combination is called the long-term variation of the process. In many cases, it's written with a simple LT notation. Long-term, LT for long-term, I guess. Pinpointing long-term variation's non-random behavior. As opposed to random short-term variation, these underlying disturbances are non-random over the long term. You can approximate them with a line, a step, a curve, or a repeated pattern. The great thing about long-term variation is that you don't have to be Einstein to figure it out. With the proper detection techniques and tools, you can see what part of your process is affected by non-random forces. If the process is to assemble a proposal, and if the critical output of that process is how long it takes to create the proposal, you want to look at the variation patterns in the output of the process. Figure 9-7 shows just the output variation, or changes in the number of incoming calls at a call center per hour. If the output metric varies in a non-random way, you can safely say that some combination of special cause factors has affected the volume of incoming calls. Figure 9-7. When we say special cause, we mean that the output has varied to an extent that is inconsistent with what you would expect from purely normal, short-term, natural, or random influences. You know that something non-random has occurred, and therefore, you know that you can find the cause and solve the problem. A good way of depicting the difference between short-term and long-term variation is in a process is by using two probability distributions as shown in figure 9-8. Notice that over time, the long-term variation is wider than the inherent short-term variation. Non-random variation is caused by special forces whose effects on the process are readily observed and understood. Consequently, this non-random variation is also called special cause variation or assignable cause variation. This one. Calculating the long-term variation of a characteristic is identical to calculating its overall variation. Therefore, the overall standard deviation is the formula you use to quantify the level of long-term variation in a characteristic. The calculated long-term variation should always be greater than or equal to the calculated short-term variation. For any long-term variation you find, you can immediately create solutions to solve the problem, whether that's conducting routine preventive maintenance on your drills, making the maintenance procedure so easy that anyone can understand and adhere to it, creating redundant systems in case equipment breaks down, or a contingency plan in the event of losing a principal leader, or whatever. Being all you can be. Entitlement. Every process involves a combination of short and long-term variation. The short-term component comes from the unaccounted for common causes, rooted within the process. The long-term component is the result of factors you can detect, special causes. Suppose that you want to reduce the overall level of variation in your process. What do? How should your new understanding of short-term and long-term variation guide your approach? Imagine you identify and remove all of the non-random special causes affecting your process. You're left then with a process that is influenced by only random short-term variation. Further shrinking the output variation is difficult. Very, very difficult. That's because further shrinking requires discovering what previously was unknown about the inner workings of your process. You need to identify, understand, prioritize, and fix the myriad of embedded common factors jiggling the process output. Okay. This hard wall in the improvement path leads to the idea of entitlement. Entitlement is the level of variation that is naturally built into a process. The amount of variation you can expect from a process under the best conditions when all the special causes are identified and eliminated. Of course, you can see that this is just another name for short-term variance. Obviously. What's the difference between short-term and long-term variation? How do you know when short-term variation is no longer short-term? No set time period creates a concrete boundary where short-term variation transitions into long-term variation for every process characteristic. The transition point depends totally on the process and the time required for long-term special causes to exert themselves on the process. Some long-term things can go wrong, assignable causes, in a manufacturing environment. Tool wear. The bit that drilled holes in your new assemble-it-yourself desk was too worn down at the time it was employed during the manufacturing process. You and 500 other people who bought desks from the same production batch now struggle to assemble your pieces while muttering unkind words about the manufacturer. Changes in machine operator. Jack replaces Jill on the printing press, but doesn't do his required maintenance. Print quality suffers, customers are unhappy, and the finger pointing begins. Differences between raw materials. Print quality also suffers non-randomly when Jill is on her shift, because the quality of the ink is sometimes compromised by the supplier, and at other times the ink is slightly off its target color value. Some long-term things can also go wrong, also assignable causes, in a service environment. Equipment breakdown. Your computer crashes, preventing you from providing great customer service at the call center. The jet carrying the express mail needs unscheduled maintenance at the airport, thus making the deliveries late. External forces. Traffic jam patterns in certain geographical areas negatively impact the productivity of a tracking company. Inventory gets backlogged, and deliveries are late. Health of service provider. The lead litigator in a very important case becomes ill and can't perform his duties. His colleagues don't have the depth of knowledge and experience to maintain the momentum created. And that is the end of chapter 9 and the end of part 2. So next video will be part 3, chapter 10.